Hello everyone, we are the MIT Lincoln Labs BeaverWorks Clinic 2019 to 2020 race car team. I'm Emmy Suzuki, and today I'll be presenting with our team PM Matthew Calagero, as well as Evan Johnson and Zoe Ryan. And before we start, we'd like to thank the people who have worked very closely with us on this project. Our team advisor, Zachary Dodds, and our liaisons, Iyasu Shimeles, HMC class of 2018, Sabina Chen, and Andrew Fishberg, HMC class of 2016. To give some background on our sponsor, MIT Lincoln Labs BeaverWorks provides early STEM education through their middle school and high school programs. During the program, students can work with UAVs, CubeSats, and miniature race cars to learn early programming skills. And in the race car course in particular, students are able to learn how to program by making their cars run autonomously, and at the end of several weeks, all of the students can test out their work in a final Grand Prix style race. And the race car course has been the focus of our project. So in order for MIT Lincoln Labs BeaverWorks to promote early STEM education for underrepresented groups, they'd like to make their curricula available to schooling systems which may not have existing STEM programs. So at the heart of our work is accessibility. This means keeping the cost of courses low and providing enough support materials so that teachers that may not have a background in STEM are still able to teach this course. So they've given us the race car course to rework so that it can be available to middle schools and high schools. And so the bulk of our work has been updating the existing hardware and reworking the software infrastructure. And on top of this, we've developed our own curricula. So throughout the presentation, we'll be going through all of the updates that we've made to this hardware and software, as well as the curricula that we've developed, and all of the extra support materials that we've created so that the course runs smoothly. And so I'd like to pass it off to my teammate, Matthew Calagero, to talk about the hardware.
Thanks, Emmy. Now, the race car that we showed previously cost $5,000. And while it's the perfect platform for a summer program that's sponsored by MIT, this cost creates a major barrier to entry for any individual or institution who wants to adopt this platform. So, in 2018, MIT began developing a prototype for a new version called the RACECAR Model Nano. Its goal was to provide most of the same functionality, but at a fraction of the cost. And one of our major deliverables was to turn this prototype into a final design. This ultimately would involve redesigning the frame from scratch so that we could add new hardware, improve robustness, and make it easier to assemble. Let's take a moment and compare the functionality of the prototype to our final design. As you can see, they have the same capabilities in terms of being able to observe and navigate their environment. We then added new hardware in 3 areas. First, sound processing capabilities in the terms of a speaker and a microphone. Second, digital electronics in the form of an Arduino, breadboard, an LED matrix, and finally a monitor directly on board the car. This addition is what we're most excited about because it improves the bandwidth of communication between the programmer and the car. For example, in Lab 2, students are supposed to recognize objects by contouring images based on color. And with that monitor, they can watch that process in real time, which makes it far easier to understand and debug. Now, with all this new hardware, you might be concerned that we lost sight of our goal of financial accessibility. But we're excited to announce that our final design only costs $100 more than the initial prototype. Part of this is due to the fact that we were able to save a lot of cost in our redesign of the frame by using more standardized parts. You might also be concerned that due to this additional complexity, it would be harder to assemble this new car. We performed a controlled study with students who hadn't seen either cars before, and we ultimately found that they were able to assemble our final design faster than the initial prototype. And we attribute this to some improvements to the design, as well as our build guide, which we'll talk about soon. Finally, we created a light version of the RACECAR-MN, which supports just the bare minimum hardware needed to get through the first phase of our curriculum. And this is over $200 cheaper than the initial prototype. Now, in order to design the RACECAR-MN, we did a lot of the designing in SolidWorks. This included designing all the laser cut pieces, as well as creating accurate models of all the purchased hardware, as you can see here. This ended up being a major time investment, but we think that it really paid off in 3 ways. First, it allowed us to rapidly iterate as we were designing the car and placing hardware in different places. Second, it allowed us to test the robustness of our design. And third, it allowed us to supplement our build guide. Now, by rolling back the model, we could show each step of the assembly and highlight new parts. Zoe will talk about how we use this to create a build guide.
In order to streamline the process of acquiring your own RACECAR-MN, the team has developed an interactive bill of materials hosted on our website. All this requires you to do is input the number of cars you want to build, as well as answer a couple questions about the types of tools you have with you at the time. From there, our spreadsheet will spit out exactly how many of each part you need, as well as where you can find them. This is a really useful tool for teachers who are trying to implement this course for the first time and want to make sure they get all the parts necessary for the cheapest possible cost. From there, you can navigate to our assembly guide, also hosted online. This is composed of 3 main parts: an introductory section telling you roughly how long we'll think this will take, as well as important things that you'll be doing throughout the process. Another section that will go over all the necessary tools and parts to make sure you have them, as well as some important information on screw tightness, which will make up a lot of what you do throughout the building process. And then finally, in the actual instructions, we have both CAD diagrams, as well as images that we've taken in our own process of building the cars to make sure it's as easy as possible to follow those steps. We were lucky to have the chance to test this out with our own students this semester and found that this kind of assembly guide was really helpful for students even with a very limited mechanical background.
Tying together all of this hardware adds a lot of complexity. But because this is an educational product, we didn't want to expose any of that to the students. Instead, we built a multi-level software stack. This allowed us to contain the finer details and complexity of working with each piece of hardware to the OS image, while still presenting an easy-to-understand and easy-to-use API for that hardware at the RACECAR core layer. Additionally, we built the RACECAR utils layer to provide any further functionality we wanted to students, either for ease of use or for educational purposes. At the core is our OS image. This is built on a specialized version of Ubuntu designed to run on the NVIDIA Jetson Nano and makes full use of its graphics processing capabilities. Installed on this image are all of the libraries necessary for making our software run, as well as a pre-built and pre-configured ROS package to expose all of our hardware to the RACECAR core layer above. Additionally installed is a Jupyter Notebook server, so that any labs making use of Jupyter Notebook can be run directly on the car from the students' personal computers. Both the Jupyter Notebook server and the ROS package start automatically to make sure setup is as painless as possible.
As Evan mentioned, the ROS layer provides us all the tools that we need to access the hardware of the car, but it can be pretty intimidating for beginning users. Thus, we created the RACECAR core library to expose a much more intuitive interface for programming the car. One of the biggest forms of complexity that we wanted to hide was the asynchronicity of the system, since every piece of hardware is running on its own clock. To do this, the main module of RACECAR core uses the start-update paradigm, meaning that users provide a start function, which is called once when their program begins, and an update function, which is called 60 times per second after that. We enforce the illusion that state only changes between calls to update by using a shift register and multi-threading model behind the scenes. Ultimately, this synchronizes the entire system to a single clock, the update clock. On top of this, we then create submodules for each piece of hardware and expose an intuitive interface for interacting with that hardware. For example, the camera module allows us to easily see the most recent color and depth image captured by the camera. With the RACECAR core library, the user now has all the tools that they need to program their RACECAR. But to make our system even more accessible to beginning programmers, we also added an optional RACECAR utils library. This provides helper functions that can process those inputs and outputs from the RACECAR core library. Let's look at an example. Suppose that a user wanted to recognize objects in an image. At the RACECAR core level, they would use the camera module and the getImage function to see the most recent image captured by the camera. And they could work with that image directly. However, they could also send that image to the RACECAR utils layer and use the findContours function to find the contours in the image, which will make it far easier for them to find their objects. Next, I'll hand it off to Zoe to talk about how we've used this software infrastructure to design our curriculum.
Here we have an overview of the curriculum for the RACECAR-MN course. The first lab is optional and gives the students a chance to build their own race car, which can save teachers time and get the students excited about the hardware on board the car. The next 5 labs focus on a specific sensor or piece of hardware on the car and do basic tasks, such as using the depth camera to have the car stop before it hits a wall in front of it. The next 3 labs are more advanced and focus on sensor fusion and things like path planning. For each lab, they have a 4-step specific setup. The first thing you do is cover a presentation, then you go into the experimentation phase where students start to actually work with the hardware, and then we go into a warm-up challenge where they actually get their hands on the code, and finally what we anticipate students spend most of their time on is the main challenge. Next we'll go in depth into what one of these labs would actually look like.
Thanks, Zoe. We'll be looking at lab 2. So say I have this picture of a rose. In order to find the center of it, I'm going to need to do some image processing. So with the correct HSV values, I can create the black and white mask. And combining the black and white mask with the original color image, I can create the contour, and with the contour, find the center. How is this relevant to the race car? Well, it's really important for line following. Here we have a picture of one of the processed images used for line following. The camera returns a colored image to us. We crop that down so that we only look at the part of the line that's closest to the car. Based on that, we can find the contour and the contour center. If the center's to the left, to the right, we can turn our race car accordingly. So now that we have a little bit of background on this, the students can work in the Jupyter Notebook that we provide for them. The Jupyter Notebook is a great way for the students to work on all of the image processing that we just talked about. And the great thing about Jupyter is that it allows the students to actually see the output of their processing, so they can tell whether their contours are looking good or maybe not looking so good. But after all of that's done, the students can work in the starter code. The starter code utilizes the start and update paradigm, so all the code run in start is run a single time, and everything in the update is run at 60 Hz. Originally, we planned to give the students a completely blank start and update, but we found that to be very difficult for the students and really non-trivial. So instead, what we provide for them is completely filled out code. Great, so what are the students actually doing? So, throughout the document, we have a lot of to-dos. We can see with this to-do, we ask the students to implement a version of line following that's a bit smoother. Because currently our solution is, if something's to the left or to the right, we're going to turn all the way left, or all the way right, which is sort of a bang-bang control of constantly shifting between left and right. So the students are able to create a version of this that's way smoother. Here we have an additional to-do asking the students to drive up to a cone and stop. This is a great stretch goal for the students to work on and prepares them for later cone slaloming. Here we have a version of one of the solutions for the code. The students control the speed of the car with their controller, and we can see that the car is able to follow the lines properly. And in addition, we can see that the students managed to fulfill one of the stretch goals, which is prioritizing line colors.
During the spring semester, we taught our course to a class of Frosh and a class of high schoolers. The life cycle of each lab began with our Frosh class. Then, we incorporated student feedback, reflected on what we thought could have gone better, and incorporated all of those improvements. The following week, we taught our revised lab to our high school class and repeated the same cycle to arrive at our final iteration. This taught us a lot and helped guide our development over the subsequent weeks. For example, we noticed students struggling with the initial software setup on the cars. Let's walk through what that looks like. Students must first set up their GitHub repository, then set up their Teams folder on the car, then connect to and set up any environmental variables on the car, and finally copy over all of their lab files before they can get started. Now, to someone seasoned with the command line, this process is pretty straightforward. It's here on the screen now with the user-specified parts in red. But to someone who's just interacting with Python for the first time, this can be daunting and even prohibitive. To combat this, we developed the RACECAR tool website. This walks students through the process of setting up their GitHub repository and helps them install our RACECAR tool command line utility, which streamlines all of the basic operations on the car. We found this greatly reduced iteration and setup overhead for students and streamlined the process of getting them up and running on the labs.
In order to assist instructors that are teaching the RACECAR-MN course, we've created a private GitHub repository that houses a couple important resources. The first thing it has are slide decks that teachers can then customize for their specific needs for each lab, and it also has lab solutions so they know what to expect when students train their main challenges. Finally, if they want to contribute to our code base, they can follow a couple guidelines that we've put online as well. Another thing we've created is a public-facing website for anybody who's excited about the RACECAR-MN. On our landing page, you can see it links you to all the things you need to set up your own car: the bill of materials, the build guide, software setup instructions, the RACECAR image, as well as the RACECAR tool. If you're a student already in the course, you may navigate to our resource section that has old presentations that you might want to look through again, objectives for each lab, as well as more description at what you need to actually do to complete the lab work. Finally, it links to our library documentation, which Matthew will talk more about next.
Thanks, Zoe. Now, a library is only useful if people understand how to use it, so we invested a lot of time in documenting our two libraries. This included creating extensive doc strings for all of our functions, describing the inputs, outputs, and including a coding example showing how to call the function. In practice, however, we saw that students found it somewhat tedious to search through these large library files just to find the doc strings, so we wanted to create a streamlined version of this documentation on our website. We also wanted to generate this automatically to save time for future developers and make sure that the two were always in sync. Unfortunately, we couldn't find a single tool which did all this in one step, so we settled on the following pipeline. First, docxypypy parses the doc strings and sends this to doxygen, which extracts semantics. For example, doxygen recognizes which parts of the doc string are referring to the parameters and which parts should be a coded example. Then breathe converts the output of doxygen into restructured text, the markdown language needed for Sphinx. Sphinx is a documentation generation tool which creates beautiful HTML websites out of this restructured text. Finally, we host this website on Read the Docs and use a Git webhook so that it's automatically updated anytime anybody pushes to our repository. This documentation is ordered by submodule and even includes search features, so it's easy to find the function that you're looking for. Today, we've talked about the hardware, software, and curricular aspects of the RACECAR-MN platform. Due to our focus on financial and technical accessibility throughout this project, we hope that people of all backgrounds, both students and instructors, will be able to benefit from this platform. This summer, Beaverworks will be teaching our curriculum as part of their Summer Institute. And after that, we hope that middle schools and high schools around the country will be able to adopt this curriculum to help increase the accessibility of STEM education. We want to thank the following people from Harvey Mudd and Beaverworks for their continued guidance and support throughout this process. We also want to thank the 13 students who took our pilot curriculum this spring. Their flexibility and feedback was instrumental in helping us design our curriculum. Thank you for watching.